Yeah, so I think you can start now. Can just confirm if my voice is clear and is everything fine. Okay, yeah, nice. Okay, so hello everyone. This is going to be our first session on differential equations. I have a test today, so I'll try to keep this session as basic as possible. This session will mostly include like the intuition for differential equations and just basic stuff about it. So I don't think you should worry much. Let's begin. We'll start with the question of why you need differential equations. You know, what is the purpose of them? They come up everywhere. When you want to study about systems where you don't know its absolute value, but you know how it changes with time, how it evolves with time. So that's where differential equations come into play. You can define and describe models with differential equations. You will see a couple of examples. The study of population. It's very hard to define or find out and the absolute population value at a particular time. It changes at a very rapid pace. So, what you do is you describe a model for it. For example, you can define the rate of births that occur, rate of death, and then you can model the population with that. It's hard to define an absolute value, but by modeling it with such differential equations, you can actually do a lot of study about it. And then you have your Maxwell's equations. They are just four differential equations that govern the entirety of electromagnetism. You know, every single thing, starting from how electrons interact and how there is some relativity aspect as well when you go that tiny, but we'll ignore that for now. You These are starting from how electrons work to how magnets interact. Everything is just governed by those four differential equations. So it's differential equations is very useful. Nature deals with differential equation. Even heat, some of you may be aware of the heat equation. That is also a differential equation. I think it involves Laplacian and all. We'll study about it. We'll talk about it. And a study of financial market. Everybody is talking about economics. Everybody is talking about finance, crypto, and stuff. And you can basically model a lot of these investment financial market things. Factors considering the investments, the trade rate, and stuff like that. You can model it using differential equations. A very popular such model is called the Black-Scholes model. You can, research about it more after the session. The point of this session is to get you into differential equations. What I want you to do is just listen to this session carefully and try. I will share this PDF. Try to explore all the keywords that I mentioned here. That way you could get to learn a lot of stuff about it. We'll move on to some introduction. You know, we'll actually see what these equations are. We'll start with a simple definition. The, the differential equation is just an algebraic equation involving a function and its derivative. It's just a function, it's an algebraic equation. It's a function of in the independent variable t and the dependent variable x dot, which is its derivative, and so on. Mm, these are a couple of examples of differential equations. You have dy by dx equal to sin x, d square y by dx square by y sin x equal. These are examples of differential equation. They talk something about the rate of change of things, right? You don't see y as a function of x. You see dy by dx as some stuff. So we'll also eventually get into how you determine the functions itself, how you solve these differential equations. That is the final part of this session. And you might notice that these two equations are very different. There is a dy by dx here, there's a d square y by dx square here. We'll also get to know how these differential equations are classified. What are the types of differential equations and stuff. These are some terms that come into play when you talk about differential equations. The first, you know, first we'll talk about order and then I'll get to degree. The order of the differential equation is the highest order of derivative of the unknown function that appears in the differential equation. So the last example, you know, this is the first order differential equation because you only have your d by dx, dy by dx term. So that is just the first derivative. The highest order involved in this equation is just dy by dx. So it's a first order differential equation. And the second example, you have d square y by dx square, which means it's a second order differential equation. And in degree, the degree of a differential equation is the power of its highest derivative after the equation has been made rational and integral in all of its derivatives. I just copied this definition from Wikipedia. I put a dagger here. I will come to what it means in 2 3 slides. You just have to wait about. There is a slight nuance here. I will talk about it in a minute. If you have these problems, I think Praveen will start a poll now for the first problem. Try answering this. Try finding the degree and order of the first differential equation. Praveen, can you start the poll? I think we'll do degree. Can you do them both simultaneously? As in both degree and order. Yeah, the poll is there. Just fill in your answers. I'll give you a couple of minutes to do this. The first one should be pretty easy. And this for the first problem here. D square by dx square plus 2y dy by dx whole cube plus 3 sin x equals 1. Yeah, I'll just wait for one more minute. A lot of people are going for the third option. A couple of them going for the second as well. I think the first one should be pretty obvious. Okay, I'll talk about the solution. The first one should be of order 2 and degree 1. That's because the highest order derivative involved in this equation is this d square by dx square. So this is an order 2 differential equation, and the degree of the order 2 term is 1. So the degree of the differential equation is also 1. And for the second question, you notice that the order is 7. That's pretty obvious because the highest order derivative here is d7y by dx power 7. But the degree, it's kind of, it's not very obvious. There is a 2 by 9 term here, and as per the definition, you're supposed to make it polynomial. That is, you need to make all the derivative terms integral and rational. But obviously, in this thing, it's not so. So, do you have to convert it first to a polynomial equation? Let's talk about it. Okay. Here comes the nuance. I'll talk about. Should one be allowed to manipulate a differential equation to convert to its polynomial form? Consider this example: y dash equals x and y dash cube equals x cube. Both these equations are same. They are equivalent equations, but this one has a degree of 1 and this one has a degree of 3. That this is you can call it a paradox. This comes with a flawed definition of degree. The definition says that you're allowed to manipulate it into a polynomial. But if you do that, it comes with all sorts of contradictions. The definition would enable this, which means you will get various different answers for the same degree, various different degrees for your differential equation. So most modern textbooks do not talk about degree at all. You know, take Thomas for example. Thomas, I think even Stewart doesn't talk about degree, and it's just an ill-defined term to be blunt about it. You don't need to worry about degree. One order gives you a lot of insight about the equation because as you know, as we'll get into solving the differential equations, we will learn that you will get some particular constants in your solution. So order actually helps you determine the number of constants in those equations. While degree, it offers no such insight into any of this. It doesn't give any value to the differential equation. So for now, I'll just ask you to forget about what degree is. It's of no use. And most of you like who are in 12th or you're a past JE, you know that there's a lot of questions on JE and 12th going on degree. It's just outdated. Don't worry about degree. It's not of much mathematical use. 1 second. I'll just have to mark the attendance. I'll give Himanshu the permission. Yeah, we'll continue. I hope you got that. And if you have any questions, just drop it in the chat. I will address it. We're now coming to the classification of differential equations. We'll look at the types of differential equations that exist. You have your ODE, which is an ordinary differential equation. PD is a partial differential equation. HD means stochastic differential equations, and there are a couple of more stuff as well. So an ordinary differential equation is nothing but an equation where your function is just dependent on one parameter. The, there's only one independent variable, y is a function of x. So you only have like pure derivatives in your equation, d by dx, d square by dx square, and so on. But while in partial differential equations, you have multiple variables to deal with. For example, you'll have something like is a function of x1, x2, x3, and so on. So there you will, since there are many variables, you will have to deal with partial derivatives as well. That's why you have the name partial differential equation. And there's types of it as well, elliptical, parabolic, and hyperbolic. I don't think you have to worry about that for now. Yeah, so the definition of ODE is just y is a function of x. The differential equation is dependent only on a single variable. And for a PDE, the differential equation is dependent on possibly many other variables, which of course results in equation consisting partial derivatives. And a stochastic differential equation involves something called the stochastic derivatives. It's very useful in finance. For say, there's a lot of models you can use stochastic derivatives with, and it's something which is more volatile. I would suggest you to search a bit more about this after the session. It's very interesting. And a couple of other differential equations you might have not heard of. These are called, one such differential equation is called fractional differential equations, and they involve derivatives like d to the half by dx to the half. It is something called d half. D here means d by dx. Okay? It's just an operator. We'll talk about it in session 2 in much more detail. For now, think of d as just the d by dx operator. That operator, you can, d1 means you're just applying d by dx. D2 means you're applying d2 by dx squared, which is the second order derivative. But what does d half mean? There's some notion for this. We'll talk about it. It's not very simple, but we'll talk about it in the next session. So don't worry about this much. And there is something of function d's. This, I think you should have encountered this in your JE thing. F dash of x is blah, blah, blah. These are functions and the derivatives evaluated at multiple points, as in, the arguments are not the same. For say, you have this, I'll go back to a differential equation. You have all these different derivatives evaluated at a particular point. Like here, you don't have it evaluated at a particular point. You have it evaluated at multiple, various different points. It's comes with its own sort of, it comes with all sort of requirements. For now, we'll just ignore them. We don't have to talk about it much. And while we deal with differential equations, we'll just uh, deal with nice functions. We don't have to worry about any of this. We don't have to worry about the definitions of f of x at different arguments. And we'll talk about the types of ODEs now. ODEs can further be classified into many types based on their homogeneity, linearity, exactness. There are so many terms here. We'll talk about it one by one. What is a linear ODE? A linear differential equation is defined by a linear polynomial and unknown function and its derivative and is of such form. So what a linear ordinary differential equation is, it's just a differential equation with all its derivative terms, all its derivative terms written as such. It's a linear combination of all those derivative terms. There is no such mix like y dash, y double dash, and y triple dash y. There's no such mixing. Every term is pure, and that's why we call it a linear differential equation. And about talk about it a bit later. The coefficients can be functions of the independent variable or they can be constants. That actually eases out a lot of things later. We'll talk about it. And this is, the example of a linear differential equation. Y double dash plus sin x y dash. It's a linear combination of all these different derivatives. And it's come to homogeneous differential equation. A differential equation is homogeneous if it's a homogeneous function of unknown function and its derivative. So, homogeneous function is right. It's something like f of x comma f of lambda x comma lambda y is just lambda power n times f of x comma y. So it's something like that. So that if that function is the independent function in this differential equation, then you call it your homogeneous differential equation. This you can also see it as a differential equation with no uh, term with just x. For say here, this example, you have something f y double dash y dash and y equals tan x. When you have zero here, you will notice that when you substitute lambda y instead of y, the equation still holds. So that's when you have a homogeneous differential equation. You can think of it like it's a linear combination of the derivatives and the constant term is just zero. The constant as in the non-y term. These are a couple of examples. This is a homogeneous function. If you put in lambda x and lambda y, you see that you get the function again. It's an example of a homogeneous function. And this is an example of homogeneous ODE. When you rearrange it, you see that it's y cube dy minus x cube dx equals 0. Or you can think of it like y cube by x cube y dash equals 0. There is no, a term with no y. The right hand, or you can think of it like the right hand side of the equation is 0. If you want to think about it that way. Now we'll come to talk about the constant terms that we encountered here. What these constants could be, the coefficients of these derivative terms. A differential equation has constant coefficients if only constant functions appear as coefficients in the associated homogeneous equation. Yeah, you have this differential equation. You notice that all these coefficients of these derivative terms and y, they're just constants. And this is just some technicality in defining it. You consider associated homogeneous equation because there's a possibility of stuff canceling out. But if you write it down clearly, you could see that all these coefficients are just constant. So this is a constant coefficient ODE. An advantage of this is it simplifies a lot of things when you try to solve it. Solving constant coefficient ODEs is actually much easier than uh, co coefficients where they are not constants and functions of x. Functions of the independent variable. And this, I think everybody would have seen this at least once. The simple harmonic motion. It is this equation is called the simple harmonic equation. This is a very fundamental equation in physics, and you see it's a second order differential equation. It's also linear because omega is just a constant, it's not a function of anything. And just to be clear, here the independent variable is time and the dependent variable is x. In this previous example, we had y as a function of x. Here you have x as a function of t. So don't get confused by that. So this is second order and it's linear and it's an ordinary differential equation with constant coefficients. It's very easy to solve this, and as you add in some more layers to this, like damping coefficients and some external driving force, there's actually a slick way to solve it using those differential operators, the D term that I mentioned before. We'll talk more about it in session two. There's actually a very, very good way to do it, and it's very slick as well. So we'll definitely talk about it in the next session. And now we'll try to solve in the most basic of all differential equations. It's a We will consider a first order linear and homogeneous ODE. This is as simple as it gets. You have an equation of form y dash plus some function of x y equals 0. It's not a constant coefficient differential equation because the coefficient of y is not constant. It is a function of the dependent variable, the independent variable. It's actually pretty easy to solve this. This is one of the most fundamental equations that you would find in entirety of differential equations. So you just rewrite this as dy by y equals minus p of x dx. And if you integrate both sides, you would see that you get something as a function of y on the left hand side and something as a function of x on the right hand side with some integration constant. We will talk about what these integration constants are, what they mean in the next session. Basically, what they are is when you solve a particular differential equations, you get a lot of solutions, and there is something called the initial value. The initial value lets you determine a particular solution from all those infinite sets of solutions that you find when you solve this. The infinite solutions is caused by this integration constant term because the constant could be just any real number. And as you move on to more advanced stuff, you can also define differential equations for complex variables, and there the constants would be complex as well, and we'll talk about it. Here's an example, and I'm pretty sure it's very easy for you to follow. You follow the algorithm, you rearrange it and pull all those y terms on one side and all those x terms on the other side, and just integrate it. You'll find that y is some constant times cos x, and when you plug in y is equal to a cos x into this original equation, you find that it satisfies the equation for any a. So you'll find that there are infinite solutions for this differential equation. And given a particular initial value, I will talk about what an initial value is in the next session. So for particular initial value, we'll find a particular solution to this differential equation. That is very useful when you That is very useful in actually like real life problems, and and you define a framework and you know the initial conditions. So you could actually determine the particular solution that the system or model follows. And moving on, you have your first order linear and non-homogeneous differential equation. The earlier one was homogeneous. This one is non-homogeneous, which means the right hand side of this equation is not zero. It's a function of this independent variable. It's a bit it's a bit more complex than the earlier one. The earlier one was a simple rearrangement and pulling y terms to one side and x terms to the other side and just integrating everything. Here it's not so simple. We will look at what the intuition is to solve such differential equations. Rearranging this, you see that you get something like this dy plus y times p of x dx equals some q of x dx. So the intuition here is that to solve such questions, just multiply some r of x throughout this entire equation, and you will try to find, you will try to multiply with such an r of x so that this LHS is just can be rewritten as the differential of y r of x. This notion may be a bit confusing. You know how this is basically a feature of Leibniz's notation for differential equation. You can pull out the dx away and you can rearrange and play with it as you want. There's a bit of technicality there, and I don't want to go too deep into it. The keyword here is that the Leibniz notation allows you to do things like this. You can pull out dx from the dy dx term and rearrange it. And you can explore more about it later. So the intuition here is that you rearrange it in such a way that this r of x dy plus y p of x r of x dx is actually the differential of some function. So here that function will be y r of x. You can see that if you multiply with such an r of x so that r dash is this, you can actually rewrite it in this way. So our goal is to multiply with such an r of x so that this LHS of this equation turns into something of d of something. This is actually something called exactness where you don't have to worry about it much, and I will talk about it at the end a little bit about it. So this r of x is also called the integrating factor. I'm sure many of you are familiar with it. When you solve this differential equation, you will find that, this is another differential equation, When you're trying to solve this differential equation, we encounter this another differential equation. This is pretty easy to solve. This r dash is just dr by dx. You pull r to this side and integrate this. You'll find that r is just e to the integral of p of x dx. P of x is the coefficient of the y term. So if you multiply with such an r of x, you will find that you can actually simplify it as so. So why, this is an indefinite integral. So when you integrate this, you'll get a constant c, and there is infinite different possibilities for what this r of x could be. For now, we'll focus for our simplicity, we'll just assume c equal to 0 always. You don't have to deal with some constant. There's just no need for that. And so this is we'll generalize it with an algorithm. So whenever you encounter a differential equation as such, you just multiply it with e power integral of p of x dx so that it turns into such a differential equation. I'm pretty sure you would have done this in your JE and you're very familiar with it. And but hopefully you got where this intuition for integrating factor comes from. And I think this is the last slide. What can you say about the existence of integrating factor? You know, how can you be always so sure that there exists an R of X such that this could always be turned into an exact differential? That is something I would leave you to ponder upon. The keyword here is exactness of differentiation. There is something called exactness. Uh, I will discuss it in the next session. Till that, I would like you to ponder over it. I would want you to find out what this exactness really is. And yeah, the try try learning about it, try researching what this exactness actually is. And yeah, that's pretty much it for this session. I'm just revisiting those slides. After this, the goal of this session is to just get you interested into all this stuff. So after possibly these 3 sessions, I would want you to research more on what the study of population is. There is something called epidemic modeling. Epidemic modeling actually involves a lot of differential equations. there is something called the SIR model, and there is just a basic model for defining an epidemic. It can model an epidemic with that. So, well, after the end of these three sessions, I hope that we'll learn enough to actually look into those models and understand it. That's our goal of this series. And for Maxwell's equation, I'm sure you can find them anywhere. And Maxwell's equation, I'm sure you can find them anywhere. And I want you to get goal of this session. I'm sure you can differential equations. I want you to get goal of this session. I will share this slide in the group. I want you to get goal of this session. I will share this slide in the group. I want you to get goal of this session. I will share this slide in the group. I want you to get goal of this session. I will share this slide in the group. I want you to get goal of this session. I will share this slide in the group. I want you to get goal of this session. Find it now. Don't we'll revisit it and now just go to the we'll revisit it and now just go to revisit it and now revisit it and now have a question in the chat. What if integrating factor becomes zero? Okay, that's a good question, but we have a question in the chat. What if integrating factor becomes zero? Even if okay, that's a good question, but we have find out that the integrating factor is what if integrating factor becomes zero? The function okay, that's a good question, but we have find out the zero and factor is what if integrating factor becomes zero? The function okay, that's a good question, but we have find out the zero and factor is what if integrating factor becomes zero? The function okay, that's a good question, but we have find out the zero and factor is what if integrating factor becomes zero? The function okay, that's a good question, but we have find out the zero and factor is what if integrating factor becomes zero? The function okay, that's a good question, but we have find out yeah, so for now, just try searching about uh, the possibility of existence of integrating factor. Does it always exist for a particular equation? And